So we'll be continuing with the discussion of problems on potential. Now, this is the thing. Using the expression for potential at any point on the axis of a ring, we have to derive the expression for field. Let's draw the diagram. Here we have a ring of radius r having charge q which is uniformly spread on its surface. We have to find the field at this point P. Now we can make a guess regarding the direction of field over here. The direction of field is in this direction, upward. Let's mark the direction. Sorry. First of all, the potential at this point P. There is the expression for potential. Now we'll mark the field. This is the direction of field. Now it's very clear that if we move along this direction of field, this distance x will increase. Field points in the direction of increasing x. So suppose from this point we move upward by a distance dx this way. Moving upward by dx will cause potential to decrease by e dx, or dv is minus e dx. dv is minus e dx. From here only we'll have e as minus dv by dx. This can be computed very easily. V is known to us. Substitute the value of v in this equation from the first one. This minus d by dx, this is the value of v from here. Now we'll take all the constant factors out. Constant factors are this 1 by 4 pi epsilon naught and q. This constant factors come out. This is what we are left with. Now for differentiating this, one thing should be clear. R has to be considered as constant over here. The only variable is x. We'll apply chain rule over here. This way. And then apply the formula. And remember, this R is a constant. This gives you this result. Final expression will be this one. This is the expression for field at any point on the axis of a uniformly charged ring. Now let's see another example. This is basically a part of theory. Here we have to derive an expression for potential. We'll derive this expression. And then using this expression, we'll try to find out the field at any point due to this dipole. So let's see the dipole first. It's diagram. This is the dipole where we have two charges, minus q and plus q, located at distance 2l from each other. And this is the point where we are supposed to calculate first the potential and then the field. So we know that at distance r from a point charge q, the potential is kq by r. So we'll try to find out the potential at this point first because of this plus charge plus q. Let us join this line and mark this distance. We have joined this line and marked this distance as r plus. R plus represents distance of this point P from this charge Q. Then some more constructions are needed over here. Let's drop a perpendicular from this B on this line PO this way. Now look at this triangle. The hypotenuse is L. This angle is theta. So this base MO or OM is L cos theta. Let's write it down over here. We'll need it. OM is L cos theta. We are basically interested in finding out this distance R plus. Now note that this PB is approximately equal to PM. PB and PM are approximately equal. Write it down over here. R plus is PB and PB is approximately equal to PM. This PM can be written as PO minus OM. PO minus OM. Substitute it over here. PO or OP minus OM. OP, this distance is R. OM we just now calculated. So this is R minus L cos theta. We have got this distance. This R plus is R minus L cos theta. So the potential at this point P, because of this charge plus Q, is 1 by 4 pi epsilon naught charge Q divided by this distance R minus L cos theta. This is the expression. This is the expression for potential at P due to this charge. Similarly, we'll have to calculate the potential at P because of this charge even. Let's again join this line A to P. This one. Now some more constructions are to be done. Let's extend this line, this PO, and drop a perpendicular this way. This line is extended. We have dropped a perpendicular. This angle and this angle, they are equal. Here even this ON should be L cos theta. Exactly in the same way. This should be L cos theta. ON is L cos theta. Again, let us take the approximation. We are interested in finding out this AP, which is PO plus ON. First of all, this R minus is equal to AP or PA, and this PA is approximately equal to PN. PN is PO plus ON. PN is PO plus ON. Now put the values. PO is R and this is L cos theta. So it becomes over here R plus L cos theta. So the distance of this point P from this negative charge is R plus L cos theta. Distance of P from this negative charge is R plus L cos theta. So the potential at P due to this charge is minus K means 1 by 4 pi epsilon naught, Q by R plus L cos theta. Write it this way. Potential is 1 by 4 pi epsilon naught, Q. This charge is minus Q over here and this one. Now to calculate the net potential at this point, we'll have to add up the contribution of this plus Q in equation 1 and the contribution of minus Q in equation 2. So net potential is sum of these two. V net is V plus V net. Let's substitute the values and simplify the expression. This is the thing, we have taken the common factors out and solve it. This becomes in the numerator we'll have 2L cos theta, and here R square minus L square cos square theta. This is the thing. Now here Q into 2L, charge Q into 2L, this becomes a dipole moment. 1 by 4 pi epsilon naught, this becomes P cos theta. Q into 2L is P. P cos theta by R square minus L square cos square theta. Now if this is a short dipole, for short dipole this R square is much larger than this term. So for short dipole we can ignore this term and our expression will simply be 1 by 4 pi epsilon naught P cos theta by R square. This is the basic expression for potential due to an electric dipole. Now we would next see how to calculate the field at this